Hello and welcome back to the Oxford Online Maths Club. My name's James and this week I'm joined by Zoe.
Hello, I'm a first year maths and computer science student.
Good to have you here, Zoe. We're also joined by some of you watching live on Thursday afternoon. You can say hi in the chat if you like, which is it's me in the top right, then Zoe, then it could be you over there. Callie is moderating chat, so maybe say hi to Callie again if you're in there. Let's see who's coming through. Aliana is in chat. Hello, says Aliana. Good to see you. Hey. We're gonna. What are we doing today, Zoe?
We're looking at multi-perfect numbers. So you might have heard of a perfect number, which is when the sum of a number's factors, if you don't count it itself, is equal to itself. But we think you can do even better than that. So we're looking at even more perfect numbers.
Excellent. Good ad for the stream. Hello, Hector and Anonymous and Aaron. Anonymous has reminded me that in Slido you can be anonymous. It's one of the reasons that we're using Slido rather than built-in YouTube chat stuff. Even if you don't have a Google account. My goodness. Right, that's also reminded me that I should do the How was your day today poll. Zoe, I don't think I told you how this works. We always ask chat how their day was on a 5-star scale.
I think I remember this from my days of watching the show.
There you go. Long held tradition. If you're okay to share, how is your day going on a 5-star scale?
Me?
Yeah, if you don't have to, but
Yeah, I mean, it went. I had a shoot that finished 20 minutes early because we got most of the problem sheet right. So that was a pretty good feeling.
oh,
And
I
then
had a tutorial this afternoon where we were in the cafe and they were trying to get rid of leftover pizza at the end. So we finished
oh,
on
that's
time, but
nice.
holding leftover pizza, which is my aim.
And then with my afternoon, I picked up a newspaper and I got the furthest through a cryptic crossword I've ever gotten without giving up.
Right.
So that's pretty
Okay.
nice.
Good caveat. Yeah. Oh, cryptic crossword. Someone told me also sort of a little bit of logic puzzle, a little bit of wordplay, sort of comedy. There's a good channel called Cracking the Cryptic, which
Yes,
uh,
yes, yes, yes. Very good.
other YouTube channels are available. But rather than promoting other people's live streams and other things, we should probably do this one. Hello in chat to Krish and Mary, who have just joined in as well. Great. Okay, and chat is having one of the best days I've ever seen. 5 stars is winning at the moment.
Fantastic.
They have. I don't know what that distribution is. Can you see this on the screen, Zoe?
I can. That's pretty good. It's looking like an exponential. Well, like a reverse one.
Yes, crucially, exponential will be weighted towards zero, right? So far, there's a couple of people voting 2 stars. I'm always looking out for people who are having a 2-star day, which reminds me that even though
Was
it's
it?
sunny and we've got some maths.
Was it not the last A level maths exam today or something like that? One of the A
Oh,
level maths exams.
possibly. Oh, if that's you, then let us know in chat, and I hope it went okay. Yeah, or
Or
if
is
you're
it
watching,
tomorrow? I know it's like this week, I think.
if you're currently in an exam and you're watching this on the replay, then I guess you could let us know in the comments. Although for that you do need a Google account, I think, having said. Right, I'm going to stop the count there because it's in this lovely triangular shape. Average 4.0, and I don't want to see it go below 4, so I'm going to call it there. Nice to know people are having a nice day. Good. Hello to Cream Puff as well. There's a minor biscuit theme this year. I don't know what the theme was in your year, Zoe, for people's usernames in chat. You could
I
be
don't
on
remember a biscuit theme is for sure.
biscuit theme is new. Right, okay. Uh, so for people who've just come in, we're going to talk about perfect numbers and then things that are better than perfect numbers. Let's get a definition on the board for what we're talking about. I'm going to put Zoe on the spot to define these things, and I'll try and type it on screen as well.
Oh,
Yeah, okay. We didn't rehearse
okay.
this.
So, you might have heard that a perfect number is a number whose factors add up to factors not including itself add up to itself, but you can equivalently say that its factors including itself adds up to twice itself. So, for example, six, the factors of six are one, two, three, and six. When you add those up, you get 12, which is two times six. Um, and a multi-perfect number is a number whose factors add up to three times itself, or four times itself, or so on, so on, so forth.
Yeah. I don't know if we want to set up some notation here to talk about the difference between the cases where maybe they're up to 3 times the number or 4 times the number. Uh, in some sense, I want to say perfect and then maybe three-fict for if it's
I like
three.
three-fict and four-fict is quite nice. Yeah.
Four-fict. Okay. I think it's going to be hard for the subtitles on this YouTube video, but we'll see let's see how that goes. So I'm going to put in here some multiple of itself. Okay, so that's our definition. We should do some examples. You gave me an example for a perfect number. You gave me the example that 6 is, if you include itself, 1 plus 2 plus 3 plus 6. Okay, we should probably have examples of other multi-perfect numbers as well, or maybe other perfect numbers, who knows. Maybe chat is aware of,
28 is it?
yeah, so maybe
28's a good perfect number, I think.
28 I think is perfect. If chat is aware of other ones, I mean, you could look them up online, but I'd be interested if people in chat just know other perfect numbers. What am I doing here? 2, 4, I'm trying to list all the factors of 28, and I'm already running into trouble. Here we go, that looks like about enough. Have I gone underneath chat? No, I'm good, I think. I've got the 1, 2, 4 for the multiples of 2, and then I've got the 7, and I've got the 14, and I've got the, I'm talking out loud. I think that's 21, 25, 27, 28, 56, I think. So this was 12.
Yeah.
That was 56, which is 2 times 28. Lovely stuff. People in chat say, further maths teacher, people visit him, so further maths exams finishing. Further maths exams finishing. Further maths paper 1 just happened for Hector in chat.
Paper 1.
Got to start somewhere, though. I guess maybe you start with paper. Maybe you start with paper 0. I don't remember. Good. Okay. So we've got some perfect numbers. They get quite a lot of airtime. Would also like to talk about multi-perfect numbers. The example.
Not sure I can think of the off the top of my head.
Yeah, the example that I put in the thumbnail is the number 120. So I think challenge for chat is to check that 120 is multi-perfect. It's not a perfect number. We might have heard of it if it was a perfect number. But 120, I claim, is one of these multi-perfect numbers. Oh, sorry, Hector's in year 12, but I've seen people doing further maths. So aware of further maths exams going on. Right. I'm going to try and do this on screen as well. I'm going to do it the slow way, and maybe for a bit of comedy, how about I try and list all the factors of 120 and add them up. I'm not great at listing or adding, and maybe while I'm doing that, maybe Zoe, you could explain a faster way of doing this.
Yeah.
Possibly so fast that I won't have listed all of the factors by the time you've explained it. But okay, here we
go. So one thing you might want to think about is when you're thinking of factors of a number in general, you can write out the prime factorization of the number. So 120 is 2 times 2 times 2 times 3 times 5. You can just find the prime factorization by looking at something that divides it, dividing it by that, and working out what derives what you've got left, and just keep doing that until you've got down to prime factors. So you can express it as 2 cubed times 3 times 5. And then when you've got that, you can think about sort of just like toggling your factors on and off. So you can have, if I've got 2 cubed times 3 times 5, I could have 2 cubes times 5, or 2 cubed times 3, or 2 cubed times neither, or 2 squared times 3, and that can be a sort of shortcut to finding all the factors. And then when you add them up, you can factorize out some things quite nicely and hopefully save yourself some time.
I love that you said toggling. That's a very
That was how
computer scientists on the stream, isn't it? I think I've almost got all of them. Do you know any tricks for me to count how many factors it's got?
Yeah. So if you look at your powers in the prime factorization, and then you think about how many ways can I select from this set.
Yeah, so I've heard this as you imagine that your factor is of this form. I mean, it can't have any other primes in it to be a factor of 120. And more than that, there's restrictions. You've said to be in this set, we get some restrictions. I can't just have all the power I want. I must have, I guess these are inclusive. at most 3 of these 2's. Now, don't get carried away. You can't start making it a multiple of 16 or 32 or something. You're limited on how many 2's you can have. You're also limited on how many powers of how many 3's you can put in this factor, and on how many 5's.
Yeah, so you just look at how many choices of A you have, how many choices of B you have, and how many choices of C you have, and hit them with a multiplication.
Okay, I've got a horrible feeling I've missed a factor. 3, 6, 9, 12. I've only got 15 on here, but I
I
think
think you should have 16.
I should have 16, right? Because checking the number of factors over here, you've got 4 choices for what you set A to, 2 choices for B, binary, 0 and 1, and 2 choices for C. You either have a multiple of 5 in there or not.
24 you're missing?
Is 24 a factor of 120?
Yeah, it's 24 times 5.
Oh, that should go in here, shouldn't it? Right, okay. Anonymous got there as well in chat. There's a little bit of stream lag, so I think from their point of view they said that before you, and we should give them credit for saying it before you. Sorry, I know that feels unfair for Zoe.
No.
Yeah, another anonymous person. Good. Yeah, thank you, chat. I didn't do that on purpose to drive engagement, but it did drive engagement. Maybe I should make more mistakes. No, I'm making enough mistakes already. Oh my goodness. So you've got this trick for thinking about how many factors there are, which I quite like, which is to think about how the factors are built. What are they made of in terms of primes? And think about your choices. So I quite like this. For the comedy bit, I'm going to try adding these up, and you're going to tell me how to speed that up. I think you did already, but I was too busy adding to. So I'm going to get you to say it again. I'm sorry.
Okay. So like if you express the combinations of all of these things as your various powers, if you express them as prime factors, then I think there are probably a lot of nice ways that you can factorize out some things and generally sort of speed the process up.
Yeah, I like the idea of factorizing this because some of the numbers I can see are multiples of 5 and some of them are not. I'm going to underline the ones that are multiples of 5. I've got a 5 here and a 10, which is 5 times 2, and I've got 15, which is 5 times 3, 20 is 5 times 4, 30 is 5 times 6, 40 is 5 times 8, 60 is 5 times 12, and then 120 is 5 times 24, the one I missed out. And that's not a coincidence, right? That this is the numbers that are not underlined plus 5 times the same list.
Yeah.
So some of the factors have got a multiple of 5 in, and some of them don't.
Yeah, and indeed you'll be so you should have exactly half of them be ones that are multiples of 5, and because it's just like your if you take the ones that aren't and then you flick that 5 switch on, you get all the ones that are.
Yeah. So the purple underlined ones are the ones that kind of have multiples, have this kind of choice down here on. Yeah, perfect. Okay. Obviously that's 6, but I'm going to leave it like there for a second. Chat, just to check that we're making sense, could chat give me another factor, a factor of this bracket? I guess it's just a number, so you could work out the number and tell me a factor of the number, but what I really want is like a factor that you know must be there based on the prime factorizations of these things. Right, we're going to give chat a moment to think about some factor, like how I've pulled out this 1 plus 5 thing here. While they're typing, I really hope this works out, because this is my claim for a multi-perfect number. I think it might be the smallest multi-perfect number. And
sounds reasonable.
Yeah, there's not that many. There's this word.
Is 120 a factorial?
It is actually, isn't it? Is it 5 factorial?
Yeah, so I know for a fact that the first 7 factorials are all more perfect than every number before them. So if this is multi-perfect, then it is the first one.
So we should define more perfect in general then, where there's a property called abundance, which is always this. Am I going to get this right? I'm pretty sure it's called abundance for the sum of the factors divided by the number. Which, if that's 2, you're perfect. If it's an integer larger than 2, you're multi-perfect. and in between, Zoe can say that you're more perfect, but larger than number
I
of.
feel perfectness is a scale, I guess.
Yeah, you've just extended the scale to say where are you on the number line to all the rationals maybe. Yeah, I like this. So people in chat are giving me factors. They have spotted, yeah, so there are factors like 2 and 3 and 4. The one I'm excited by is when Anonymous says 1 plus 3.
Ooh,
That's
good
the one that I'm
thinking.
really excited by, because maybe they've spotted that some of these numbers are multiples of 3. It's associated with whether you chose to put a factor of 3 in your factor or not. And those are multiplied by 1 plus 2 plus 4 plus 8. And isn't that nice? At the end there.
Nice.
Let's write down the 1 plus 5 to make this a true statement. Oh, I don't know if people in chat noticed, but I wrote some incorrect equals signs. It was not an intentional mistake. Over there, it's really bad. I said that 6 was equal to 12. Someone's got to stop me if I do nonsense like that. I've got one here as well. Okay. This is really nice. Possibly when you see this, yes. So it's also a multiple of 5. I think that's true. But the point that I want to make is that something like this happens in general. That if you have a factorization, if you know the prime factorization of a number, then the sum of its factors always looks a bit like this. Exercise for chat, I suppose. What do I mean by a bit like this? And there's something going on with this 1 plus 2 plus 4 plus 8, which maybe you can generalize. So I'll give chat a moment to type, how does this generalize? What do we do? If we want to write down the sum of the factors of something else, it'd be nice if I could skip straight down to this factorized form, right? Multiplication is faster than lots of adding. And I think for the rest of this episode, I would like some sort of nice, fast, factorized form to work with. So I'd like to get to the point where everyone's happy with what's going on there. I'm talking quite a lot. Zoe's got tea though, so this is good.
Sorry. Yes.
No. What's your tea? What have you got?
We've got a green tea today.
Oh, very good. I've got a bottle of water because I have drunk too much tea and coffee already. Yeah. Right, hang on. Yeah, so let's go. So Anonymous has got a question which I want to come back to in a second. Aaron's got a question because simultaneously Joe and Hector have put a generalization or some idea that if you find
that.
Yeah, it's almost, isn't it? So it's prime factors plus 1. Like there's a multiple of 5 in our number, so 5 plus 1, there's a multiple of 3, so 3 plus 1, except there's a subtlety here, right?
Yeah, we've got a 2 gone rogue somewhere.
Yeah, it's not just 2 plus 1, it's 8 plus 4 plus 2 plus 1. So we've got to get some understanding of what's going on there. I'm worried. What would happen if it was a multiple of 7 cubed? We'd get some sort of factor in our factors. And I'm going to try and get us to a point where we can guess what that would be. So plus more stuff sometimes. Okay, good. And then questions. Anonymous says, if it's a perfect number, then all its primes plus 1 multiplied by each other gives the number, and that's close except for the same thing that we're talking about, that sometimes it looks like it's not just prime plus 1. Over here I can see prime plus 1, but also prime squared and also prime cubed in there as well. But yes, so then perfect. If this turns out to be twice the number you started with, then that's a perfect number. And then what did Aaron say? Aaron had a question as well. The rule for all first times, any one of you have to add m plus m minus n to n minus 1 for perfect numbers. Okay, we're refining that at the moment, aren't we?
Oh, this next one looks good in the chat.
Yeah, there's things coming through chat. Can you see chat as well? Good. Can you see chat over the
It's a little fuzzy. I can work out what they're saying.
Okay, that's nice. You get the gist of the maths.
Yeah. This is where I'd bust out the sigma notation, but I'm not actually sure if we're allowed to use that.
I actually tend to be quite chill. It's 5:30 on a Thursday. Yeah, I like this. People describing it in words, I think is It's probably better for us anyway. If you get the sigma notation out, then you might be out by 1 or something. But yeah, there's this observation that in this case the number's got a factor of 2 cubes in it, and you're supposed to add together all of the powers of 2 until you get to 2 cubed. Because Zoe, do you want to do the because?
Yeah, so if you sort of look at your prime factorization where you have 2 to the a times 3 to the b times 5 to the c, and you think about say you sort of like you consider all of your options for b and c, and when you've expanded it out, um, you're going to get 2 to the 0 times all of your options for b and c,
Yeah, it is.
plus 2 to the 1 times all of your options for b and c, uh, plus 2 to the a, 2 to the 2, and all the way up to 2 to the a times all your options for b and c. And then you can extend that into looking at 3 to the 0 times all your options for c, and stuff like that. And it's sort of intuitively, I mean, to me, it kind of makes sense where this is coming from.
Yeah, we've got more choices for how many 2's to put in our factor, and when we've got different separate mutually exclusive choices, we tend to get a sum of different things. So we've got these different terms that represent the different choices, and it goes as high as the highest power that you're allowed to have for that number. There's got to be an 8 in here because there's an 8 as one of the factors. Let's quickly check. So this does turn out to be 360. Which I would do by multiplying these things together rather than by adding together these 16 things. My goodness. Let's do a quick check. So let's do the sum of the factors. I'm going to pick a square number, I think. 36. Squares are nice because they have an odd number of factors. You can work out why that is now. I mean, maybe you know why that is already, but squares have got an odd number of factors. So I think 36, by the way, is 2 squared times 3 squared. That's not really a factor tree, is it? But I tried. It's been a long time since I did a factor tree. Anyway, so I think it is. My factors might be odd, or they might be even, or they might be a multiple of 4.
Yep.
And sort of separately, like an independent choice, is they might be not a multiple of 3, or they might be a multiple of 3, or they're even allowed to be a multiple of 9. That's how many 3's you're allowed to have in your factor. So I think this is the sum of the factors. If you like algebraically, if I multiply this out, every term I get will definitely be a factor of 36 because I haven't got too many 2's or too many 3's or any other weird primes around. And even better, every factor of 36 has to appear in there somewhere because it'll have some 2's, it'll come from one of these, and it'll also have some 3's, but not too many, and that'll come from one of those. So if you multiply that out, you get precisely all of the factors of 36. So bijection. Good. I should probably check this or something, shouldn't I? 4, 5, 6, 7. Oh, yeah, okay. Mumble. What is this then? 7 times 13?
Yeah, which is 91.
91. Okay. I suppose if I'm checking this, I then also work out all the factors of 36 and add them up and get 91. Oh, good. Someone in chat's done it. Thank you, Krish. My goodness. You've saved me so much time. My goodness. There you go. Oh, they've done the same thing as me, though. They've done the same thing as me. Okay.
It's probably correct.
It's probably right. But to be totally convincing, I should probably now write out all 9 of them and add them up very slowly and get 91. I'm not going to. Hopefully this makes sense as the sum of the factors. When you do A-level maths or equivalent, at some point you learn a rule for adding up sequences like this. So a sequence where you have powers of a number, 1 plus 2 plus 4. That's called a geometric series, and there's a simple rule for adding them up. But I think today, maybe we don't need that today.
I also can't remember what it is off the top of my head, so I'm happy to say we don't need it.
We're gonna leave it. We're gonna leave it like that today. Good. Yes. Is it kind of like binomial expansion? Yes. Should we talk about this?
Yeah. That sounds good.
Yeah, because, and they're saying like binomial expansion because um, there's this link between expanding brackets versus making choices. Um, I don't think it gets highlighted in school very much, but if you learnt a method for multiplying out brackets that's like, I don't know, you need to do a plus b multiplied by c plus d. I'm being very algebra centric and using 4 letters. I'm sorry, that's just how I am. Um, I think some people learn this technique for multiplying this out, which is called FOIL.
Yes, yes, yes.
Yes? Good. First, outside, inside, last. Ooh, I can't draw that without some of the lines crossing over each other. That's made me think about something different. Yeah, never mind. Okay. First, outside, inside, last, which I think some people learn as like a recipe, just like go and do this thing, first, outside, inside, last. There's a way to think of that in terms of choices. Zoe, do you know what I mean? Or...
Um, I'm not exactly sure what
So
we're.
uh, the link I'm trying to make is that this idea about making choices about how many powers of 2 you have, choices about how many powers of 3 you have, and the fact that I haven't done it on screen, but if you multiply out all of the brackets over here, if you multiply all of the terms, then you get all of the possible choices for something from this bracket and something from
Right,
that bracket.
yes.
Like a kind of menu choice where you need to choose something from the first bracket and choose something from the second bracket. Pick your starter and your main course, multiply them together. There you go. That's a mixed metaphor. Yes, good. Okay. So this first outside inside last thing, what it's really saying is it's every combination of choices where you choose something from the first bracket and you choose something from the second bracket, like a menu. And that's why there's 4 letters in the acronym, first, outside, inside, last. The 4 letters are because you have choices about what to take from the first bracket and choices to take what to take from the second bracket. That generalizes beautifully that when you multiply out brackets like this, even with lots of terms in the brackets, the things that you get are all of the possible choices of one thing from each bracket multiplied together. This is a good way to think about what's going on when you do a binomial expansion. You get these coefficients called the binomial coefficients, but also those are the same numbers that you get when you do combinations or choosing or counting the number of ways to choose things.
Someone has said a over 1 minus r is our way of adding them up, which so is you're thinking along the right lines because that is the sum of a geometric series, but that is specifically if you have an infinite number of terms,
Yes.
and a bunch of other restrictions.
So cream
And
puff is a finite series.
yes,
Oh,
we've
it's
got a
gone. Oh, okay.
finite number of terms here.
It was, yeah, no, it's good. Okay. It's maybe highlighted your point about like, yeah, I'm pretty sure there's a formula for this, but they are now hopefully typing the finite series version of that formula. So that,
There's like something with like a r to the n minus 1 or something like that. I can't exactly remember what it is.
yeah, I'm going to do a plug for a different live stream, which is this is on the MAT syllabus. So in about 2 months' time on the MAT live stream, we're going to do some revision about geometric series, about adding up some things. Hector has done the long addition and has heroically got the number 91.
Oh, fantastic.
There we go. And an
And
anonymous
there's
person.
there are 9. Yep, there's 9 numbers there. I believe it.
Yes. Oh, 9 numbers because you have 3 choices for what to have as a starter. Separately, you have 3 choices about what to have as a main course. 3 times 3 is 9. Yeah, okay. 9 things. Ooh. Yeah, Joe's correct, I'm afraid. I can't run both of them at the same time. So this runs for a couple more episodes and then turns into Matt live stream in the same slot. Right, okay. We've got one example of a multi-perfect number, which I like because it's 120, so it's a little bit better than 100. And we've got a couple of examples of perfect numbers. I wanted to tell you some facts about perfect numbers and multi-perfect numbers. We've shown you this example where the number is 3 times itself. There are, and this will sound stupid, there are at least 6 of these numbers where the sum of the factors is 3 times the number itself, and probably only 6. So I'll give you a list of, I'm calling these 3 perfect or 3 fict, I think. nobody knows how many. Like, nobody's proved that this is all of them. But the list is maybe 120, 672. Oh, I've committed now. I'm going to have to write them all out. And I've started saying them out loud. So, oh my goodness, 523,776.
That's a step up.
It's a bit of a step up, isn't it? 3 digits, 3 digits, 6 digits. Oh, I've not written these.
How long's the next one?
9 digits.
Okay.
459,818,240. It's certainly a number. It's the sum of its factors is 3 times as large as that. And then the next one is larger, but maybe not as much larger as you might expect. It's 1,476,304,896.
Nice.
And then the next one is a bit larger again. It's 51 billion. 1,180,160.
How confident are you that these are the only 6, would you say?
Well, pretty confident. People have been looking. They're not that large.
Yeah.
If you're doing a computer search or something, then probably you can check some more numbers. And the most recent discovery, I don't know for sure that was the largest one, but the most recently found one was about 400 years ago. That's not a proof, but that's me saying that for the last 400 years, mathematicians have been trying to find another one and haven't found one. And I suppose if you accept that line of reasoning, then Andrew Wiles could have just said, people have been trying to prove Fermat's theorem for ages. It's been a few hundred years, let's just call it a day, guys. So it's not good enough for mathematicians, but they're not that big, and we've been looking for them.
I won't go getting a tattoo that says there are 6 3 perfect numbers.
Right, yeah, you're good to know that your rule for tattoos is like mathematically proven. So no one knows, but they think there might be just 6 of these. In fact, people think there might be. Here are some more conjectures, which are baseless speculation at some point, right? That's an overstatement, but maybe I stand by it. People speculate that there are finitely many of them for each number, in the sense that there are 6 3 perfect numbers. Maybe another one really large out there just for fun, but finitely many. People speculate, and people speculate that there are finitely many 4 perfect numbers, finitely many 5 perfect numbers, and so on. And they also think that there's at least one of each sort, which is quite a lot further than we've actually found, because the furthest we've gone is we've got an example of an 11 perfect number, a number where the sum of the factors is 11 times the number, but nothing more exciting than that. Like, we haven't found conjecture that it keeps going forever, that there is a 12 perfect number, nobody's found one, and conjecture that there's only finitely many of them. So we haven't found any, but people suspect that there's at least one and only finitely many. I sort of feel like those two conjectures are a bit opposite of each other.
Yeah.
It could be.
It feels like if we can find a 7 million perfect number, why can't we find another 3 perfect number?
Yeah. And for perfect numbers, well, we keep finding more and more of them, don't we? Well, that's an exaggeration as well, but there was a recently discovered new perfect number, which is huge, but sort of feels like there's a bit of a pattern to roughly how large they are, and that there might be some more out there. I think nobody knows that either. So there's loads of questions here. There are kind of really. The next question you might ask is sort of, how many of these are there? How large are they? And people have got no idea. I quite like maths for that reason, right? That you can do this kind of like adding the factors together, and you say, oh yeah, there's a pattern here, there's something going on, and then you say, well, obvious question is what's going on, and people don't know. Okay, so I think what I'd like to do, and I'm not going to write down the 11 perfect number that people have found, or any of the enormous ones that people have found. They've found some really large numbers. If you just want a large number, there are some examples of that. There's very, very multi-perfect. Instead, I thought we would try and construct one. There's this technique
Yeah.
for constructing them that
Someone's just asked, are computers discovering these new perfect and multi-perfect numbers? And they are, but so can you. And here's how.
good lead up. So I made it sound like computers are checking every single number, but if you just want to find an example, maybe not the smallest, but you just want to find an example, there is a thing you can do to try and build one yourself. A sort of build a bear approach to multi-perfect numbers. Zoe, do you want to explain how you do this? Maybe starting
Yeah.
with 2 to the 8.
So starting with, sorry,
Maybe 2 to the 8 or maybe 2 to the 9. It's your
I like
choice.
2 to the 8. I like 2 to
Okay.
the 8. So pick your favorite power of 2. Decently large, but not like ridiculously large. We'll do 256, which is 2 to the power of 8.
Okay, so 2 to the 8 is 256. Okay.
And the neat thing about working out now you need to work out the sum of its factors. There's a neat trick when you just have a single power of 2, is that it's going to be 1 less than the next power of 2. Because if you think about the expansion, you have 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. And if you think about, like, those of you that have done binary, well, that will seem familiar too. But if you add all these up, you'll get 1 less than the next power of 2.
Yeah, this is like a binary overflow thing, isn't it? If you added one more 1, if you added one more,
But then we'd need another digit,
it
yeah.
would tick over to 2 to the 9. Right, okay, very nice. In binary, 1, 1, 1,
So,
1, 1, 1, 1.
the sum of the factors of 256 will be 511.
Okay, let's check the ratio. Maybe there's a perfect number already. I mean, maybe not, but let's check the ratio. Okay, live update on the ratio. It is 511 divided by 256.
Which is nearly 2.
It's nearly 2. The powers of 2 do this to me, that they get very near to 2. They're almost perfect on their own.
They get infinitely close to 2.
They get as close to 2 as you like, but on their own they're not perfect numbers. There's a
Yeah.
way to make them into perfect numbers with some conditions that, I mean, that's how all of the perfect numbers we know are of the format 2 to the power multiplied by something. We're going to do something like that because we're going to multiply this by something else.
Well, 511 is 73 times 7.
Okay, you've done some
Uh,
factorization there.
yes.
That is not obvious. Wow. 7 times 73?
Yeah.
490 and 21. Yeah, okay.
And so now 73 is quite an ugly number to have on the numerator. So
Yeah.
we can multiply it by another fraction.
Okay.
This time we can put 73 downstairs.
Yeah, so the idea, I suppose, then, okay, so you're going to try 2 to the 8 times 73. 73 is prime, I think. Yes, that's why you factorized it like that. Okay. So we could keep it, yeah, okay. So to try and get rid of this 73 in the numerator, you're saying we should try this number with the 73 in here as well, because in the ratio, if the number contains 73 itself, then up here, downstairs as well.
Exactly.
Right. So live update on the sum of factors then. The sum of factors is now 511 times 1 plus 73.
Okay. So now we've got a 74 upstairs.
Yeah, okay, let's have a check on the ratio. So the ratio is 511, which I'm going to write as 7 times 73. And downstairs 256 times 74. So I'm being a little bit clever by trying to write this in terms of its factorized form I have forgotten to factorise 74, but bear with me. The number itself is 2 to the 8 times 73, so it's down here. And the sum of the factors also factorises into a bit due to all of the 2's and a bit due to the 73, which we agreed before. The sum of the factors, you just get this bracket, 1 plus 73.
And we're a bit larger than 2 now, aren't we?
We're doing all right, aren't we? So this feels like progress because, well, the 73 is going to cancel.
We've multiplied it by like a fraction that's greater than 1.
We've nudged it a little bit larger. The ratio's gone up a little bit because we've put this extra
Yes.
prime in. In general, if you are hunting for a multi-perfect number, and you have something where it's a little bit under a whole number, you want a whole number, you can multiply it by an extra prime. Well, a fresh prime will give you a fresh bracket of like 1 plus p in the sum of factors, which might be enough to nudge it just up a little bit.
So now we've got 74 is 2 times 37.
Oh yeah, okay. That's quite nice. Let's label that. That's not over
So
there.
any sort of big number on the top will have to also be on the bottom because there's no way we're going to be able to discover a 37 perfect number.
Yeah, that feels quite ambitious. Nobody's discovered
Yeah.
a 37 perfect number. Challenge for chat, I suppose, is to take the other route. We're trying to cancel out factors to try and bring this down to being a whole number. It's quite tricky, right? Because every time you introduce a new prime, introducing a new prime into the number as you start searching these things, the new primes all appear in the denominator because you're doing the ratio, right? The sum of the factors divided by the number itself, and the number itself has got maybe some weird prime factors. So you have to be careful because those weird prime factors downstairs kind of stop you from being a whole number unless they also appear upstairs. So for our next trick, I think you're saying we should bring in a 37.
Yes.
Okay.
And as that is prime, we'll get 1 plus 37 on top.
So I'm going to spell it out again, sorry. Sum of factors.
Right.
We're doing good for time, so I'm going to keep going. So sum of factors is this bracket from all of the stuff to do with the powers of 2, and then this bracket because of all the, you have the option to think about factors that are multiples of 73 or not, and you have the option to have factors that are a multiple of 37 or not. So live update for the ratio. Let's factorise that thing again. So this 37 is going to give me, 37 downstairs. And it's going to give me 38 upstairs. I'm going to write that as 2 times 37, sorry. This feels like the sort of moment where someone in chat might say, what is happening? And it's not obvious that this is going anywhere.
We're just sort of trying to nudge our ratio towards the next biggest whole number, I suppose.
Yeah. So there's going to be a way to generate an enormous number where, if we're lucky, then this process will terminate. And we've now got a number that is 2 times 19, which feels like we're making progress. We're discovering factors of something.
Yeah, we're getting these sort of factors on top lower and lower and lower.
And maybe eventually we'll be at the point where the things downstairs are all cancelling things upstairs and we're left with a whole number.
I mean, let's throw 19 in there.
Sure, yes. It's not currently happening, is it? I've just checked. I suppose I should be checking if these ratios are whole numbers or not, and I think it's not yet because we started with loads of 2's and we haven't cancelled them all yet. The idea, I suppose, is that we play these games and keep being careful with which primes we include. Yeah.
Trying to play until we run out of 2's, basically.
Yeah, because we need to get rid of all these 2's. It's quite a strange method, isn't it? We started with a big pile of 2's and we're trying to get rid of them all. Okay. What's next then? 19. Okay.
Yeah, I'd throw 19 on there. We have, I think, 4 steps to go, including this one. So,
Should I speed up? No, I'm having fun.
I don't know if you want to write it out long form every time you can.
Let's skip to the ratio. Let's see if we can skip to the ratio. I'll start skipping steps. Does it get easier towards the end? I think it probably does. But
yeah, the numbers get smaller.
okay. Sneak preview of my challenge of writing on the board. I think I do want to do all of them though. It's becoming a sort of art form thing. 37 downstairs, and then if you put a 19 in, then you get 20 upstairs. 1 plus 19 in the sum of factors, which is 2 squared times 5.
Now let's take a look all the way back at our start, because now our largest unaccounted for factor on the top bit will be the 7.
Oh yeah, you have got the 7. And if I put the 7 in, then I'll get just 8 upstairs, which is quite good because it's going to kill off some of these 2s that I'm trying to get rid of. Can I put the 5 in as well? I think it's not
throw the 7 and the 5.
1, 2, 3, 4 2s upstairs. I've got to get rid of 8. So the putting 7 downstairs will give me a few more 2s upstairs. You're going to throw the 7 and the 5.
Yeah.
So we're making an enormous number, but it kind of feels like we're making progress.
Number is going to be quite big.
It's going to be quite a large. Okay, live update on the ratio. Oh, I'm going to draw the line in as well. Live update on the ratio. It's all of the stuff that it was before, but with an extra little factor. Oh my goodness. Yeah, we're doing it. It's going great. Is my computer happy? It's not entirely happy with the numbers. That's not quite what I meant by computer-aided search, but here we are. 2 cubed over 7, because we get p plus 1 over p, and then
2 times 3 on 5.
Oh, quick check, because it feels like that could be the 73s. If you work out this ratio, the 73s cancel, the 37s cancel, the 19s cancel, the 5s cancel. And there's loads of 2s. There's 1, 2, 3, 4, 5, 6, 7, 8 2s.
We currently have 3 divided by 16.
I think we've got loads of 2s actually. I think we might be done.
Hang on.
We're done 1, 2, 3, 4, 5, 6, 7.
We're not done because we've got a 3 on the top we need to deal with, don't we?
Oh.
2, 3,
I think that's
4.
a 3 perfect number.
Hang on. 1, 2,
There's this
3,
general fact, by the way, which we'll do in a second. I think that's 3 perfect. Hector in chat thinks it's 3 perfect.
Oh yeah, no, I agree with you. Yeah. I think that we've hit it.
It's a 3 perfect. And I'll do the general fact in a second. But this huge number, we didn't have to check all the numbers in between. And I don't know if it's the smallest. I suspect it might not be.
Can I suggest?
Ooh,
just
try
throwing that. Just try throwing that 3 in the denominator.
Yeah. So there's a general fact that if you have a 3 perfect number that's not already a multiple of 3, bit of a tongue twister, right? 3 perfect, but not a multiple of 3, then you can consider chucking in a 3 to multiply your number by 3, and of course, well, that makes the number 3 times as large, but it makes the sum of the factors 4 times as large. The 3 plus 1 in brackets that chat told us before. So you go from a 3 perfect number to a 4 perfect number.
Which is kind of fun.
So with this one, you have the option to then, as a final party trick, also multiply by 3 to get a 4 perfect number instead.
I think we should, because I know what it gives you if you multiply by 4, and I don't want to bother dividing this by 3 right now.
I need to multiply by 2 to the 8. This is 459,818,240, which is
459,818. Look at that.
240, which is one of the ones that was known back in 1643, but is one of the ones on the list.
Was it one of the ones on our list earlier?
Well, it's conjectured that our list was complete. So we haven't discovered a new 3 perfect number, but we have followed a kind of iterative path to end up at 459,818,240, which was what was it? List. This one.
Oh, fantastic. Look at that.
There it is. So you could discover this without having to check all the numbers in between. Of course, if you want to know the 3 perfect numbers in order, then you should check the numbers in between as well. Good. Okay.
And do you want to see the? Should we see the 4 perfect number that you get?
Yeah. So you did this one before the stream.
I did this one a while before the stream. I think I did this one
before the stream.
I would say about 18 months ago.
Right. We had a separate conversation about multi-perfect numbers quite a long time ago. This method can go wrong. So If you put a prime downstairs, you can't then use it again. Or if you do, then it changes history and it changes the sum of factors thing that was going on. So if I had another 37, I could write 37 squared instead down here. But we've agreed that when a prime is to a power in your factorization, non-trivial power, that the sum of factors, the bracket upstairs, the sum of factors should be 1 plus prime squared. So there's kind of an extra thing going on up there. So this method can run into a sort of dead end.
Mm-hmm.
Kind of has to. If this always worked, then we would run this for all of the powers of 2, just seeing what happened and generating loads of new stuff. Actually, people are doing that a bit, but you can do this. Right, should we try 2 to the 9 instead?
Okay, yeah.
So, just as an example, I had a go at this one just before the stream, and 2 to the 9 has the sum of those factors is 1023.
Yes, that's definitely divisible by 3.
Yeah, and then it was a bit of I had to put it in Wolfram Alpha to factorize it. Oh no, I didn't. I divided it by 3 and it was 11 times 31.
That sounds about right to me.
So I could aim for an 11 perfect number, right? And the largest we've got is 11 perfect. So I could leave the 11 upstairs in this sum of factors and just say, oh, I'm going to keep that there. That's going to be part of the answer. I don't have to cancel things from the numerator. If it makes an integer, then I'll stop.
It's almost like sort of pushing your luck, where you're like, do I want to go for a big one or just get myself closer to something nice?
Right. So I'm gonna, I think, not look for an 11 perfect number live on stream. Feels too ambitious.
Probably fair.
What I tried instead was, okay, so try 2 to the 9 times 11 times 31. I checked halfway, wasn't working, so I went to this one as well. The sum of the factors is now 3 times 11 times 31 times, and then I get, from the 11, I get this factor of 12 upstairs, which is 2 squared times 3, he says, looking at notes, and 32, which is 2 to the power of 5. Which feels pretty good, except downstairs I've got 2 to the 9, right? So I've got 2 to the 9 over here. I've got 11 over here, and I've got 31 over here. So what next, I suppose?
We've got 2 3s on the top.
Oh, 2 3s. Oh yeah, we've got 2 3s. We've got 3 here and
maybe
a 3
we can
there.
sort of deal with them both at the same time.
Yeah, I was torn on this because you could go and have a look to see what happens if you leave one of them alone. So you could say, no, I'll only put one factor of 3 in here, and the other part is going to be part of this thing that makes it a 6 perfect number or something, or keep the other one around. I wasn't that brave, so for 3 squared, I should try and cancel things to get more powers of 2. Although I say now, if I put 3 downstairs, then
You're the 4.
4 upstairs, which is not enough 2s for me to be done, right?
No.
Oh yeah, it is.
Is it?
Wait a second. If I put 3 downstairs, what happens?
Do you just get a 3 perfect number?
Maybe. Maybe I do. Okay, hang on. 2 to the 9 times 11 times 31. If I was brave and went for 3 downstairs, yeah, I get one of the other 3 perfect numbers, 523,776. Oh, I didn't realise I could do that. Okay, choice then. We can try and go down the route where having 1 3 downstairs. Oh, I've had 2 3s downstairs. I didn't believe. I should have believed. Huh, interesting. I missed an opportunity to discover a 3 perfect number. Where am I going with this? Am I trying to find a 4 perfect number or something?
I think if you put a 9 downstairs, you get a 4 perfect number.
Okay, you've chased through what happens next. 11. I've still got this stuff. 2 to the 5 over 31. And if I put 3 squared down here, then upstairs, this is the thing we were talking about, I get 1 plus 3 squared. for the options of what the factors might be. This number is huge. It has loads of factors. Some of them are multiples of 3, some of them are multiples of 9, but those choices are kind of independent of the other factors that might or might not be there. Gives me a 13 up here. And then I just sort of chased that away. So having 13 upstairs, I put 13 downstairs. So I tried this times 13. I'm just going to be cheeky and write on the board like this. So 13 downstairs gives me a 14 upstairs. And then I'm still not done because I need to keep playing to get rid of the 2s. So 1, 2, 3, 4, 7, 8 2s. I'm not quite there. I need to play a little bit more. But if I put a 7 downstairs, again 8 upstairs, my number is now this. And its sum of factors looks like this, which I think when the dust settles is 4.
I think it is, yeah.
11's cancel. I did both the 3s. Both the 3s.
You've got 2 to the 12 on top.
To 11. I think I got 2 to the
No,
11.
2 to the 11, yeah.
2 to the 11.
Sorry, 2 to the 11.
Which then 2 to the 9 downstairs gives me 4. Stop. 4, perfect. Good. So this is quite a fun game. If you put larger powers of 2 in, you can. It's a kind of exploration thing where you can go and find different factors and see can you make this large number. You shouldn't repeat factors unless you're willing to do this kind of like 1 plus 3 squared thing downstairs. So that's an example where other than the power of 2, the number is not square free. It's fact that all of the 3 perfect numbers we know have no repeated prime factors except for the number 2. Which means that they're amenable to being discovered like this, of just trying adding in extra prime factors until you found all of them, without having to worry about squares of prime factors. It's not known if that's the case in general, or if that's true for other perfect numbers. There we go. So Hector's calculated in chat. Right, and Joe's got the $1 million question, I think. Does this work if you start with something other than a power of 2? Which is a bit like saying, all of the things we're discovering like this are even numbers. Very even in some sense, loads of 2s. You might know that all of the perfect numbers that people have found are even. It's also the case that all of the multi-perfect numbers that people know are even, and nobody knows whether any odd multi-perfect numbers exist. In some sense, no, yeah,
The one that's just been put in chat is indeed 4 perfect.
Yeah, I think it's our number. I think they might have calculated
Is it our number? Oh, I see.
Possibly.
I see. I made a little script to quickly check the perfectness of a number.
Right. Oh yeah, because we haven't said your fact, which is, well, you mentioned it, but we should do your fact. You've been looking at, out of all of the numbers, if you go from 1 and count upwards, which is sometimes you see a number that is more abundant than anything you've seen before, more perfect than anything from before.
And the first 7 factorials are all examples of that. So, I mean, 1 just has a ratio of 1. 2 just has a ratio of 2 has a ratio of 1.5. And then when you get to 3 factorial, that's 6, right? Your third perfect number. 4 factorial, here we go, has a ratio of 2.5. And then 5 factorial, 120 is our first 3 perfect number.
And not only is it 3 perfect, it's none of the numbers smaller than it have ratio larger than 3, which is kind of weird.
So they're all like basically all of the factorials are like new like champions of like the highest ratio we've seen so far. But this breaks because 27720 has a ratio of 4.052. Whereas 8 factorial, which if I recall is 4320, has a ratio of 3.95. So it's lost.
So there comes a point where if you want to make something very abundant, to have a huge sum of factors, then sometimes you should just look at the next factorial number, and sometimes you should do something different.
Yes.
And it's interesting to me that 7 is prime, and 8 is really not prime.
Yeah, it's like the least prime of those. Yeah.
Yeah, yeah, sure, I know what you mean. So when you multiply by 8 to get up to 8 factorial, that doesn't affect the sum of the factors very much.
Hmm.
I mean, it makes it larger, but only because you're changing the bit to do with the powers of 2 in your prime factorization. Whereas I think if you multiply by a new prime, like 11 or something, then, or that unlocks a whole load more abundance because you get this new factor in your sum of factors.
Yeah. If I was to take 7 factorial and multiply it by 11, I would get what is 7 factorial?
Oh gosh, huge, I think. Is it 5,040? I'm holding a
That sounds
calculator.
right.
Yeah, okay.
Yes, if you were to multiply by 11 instead, you'd get 4.19, which is certainly better than 8.
Right, so multiplying by prime would be better. I feel that's unfair though because I've multiplied by quite a large. Well, I guess large primes is what is large prime is a smaller nudge because p plus 1 is not that much larger than p as a ratio. Okay, interesting. Right, good. You were looking into this because you were trying to prove that abundance is unbounded, which is a
Yes, which is still a problem I'm not 100% sure how to do.
yeah. It must be known because people are out there making conjectures about multi-perfect numbers existing for all k, but
Yeah.
don't look at it. Keep trying to prove to
So
yourself.
I've been like plotting graphs of perfectness versus like well size and seeing how it scales. And so far it looks like it's unbounded but growing incredibly slowly. Like it almost looks like logarithmic in a way.
Yeah. I think I know a fact about prime numbers that's helpful, but I think it's in third year maths, so I'm not going to tell you it. Um, I think the answers are out there, but part of the fun of this, I think, is exploring for yourself. This is the thing about being a student that loads of like you still have things to discover and things that you can go and explore. People are doing that, I think, at school or equivalent, getting ready for university, but also when you're at university and even when you leave university, there's still stuff to explore and discover. Even if someone's already found it in 1643 or something, you can still get a lot out of going and looking for it yourself as well. Good. We're at time, I think. So I'm gonna think wrap up the stream. Thank you very much to chat for joining in and helping add to 91 and multiply numbers together and reminding us how geometric series work. I do recommend that you have a mess around with this. You might not discover a new multi-perfect number, or you might discover a multi-perfect number. That's quite fun, knowing a fact about, in our case, this enormous number that the sum of factors is exactly 3 times the number itself, by construction, as an alternative to doing a big computer search. So mess around with this. I'll put a link in the further reading notes for a more detailed description of the method of what we're doing here. So check the further reading notes on the Maths Club website, link in the description and on screen, if you want to see further reading notes for a kind of report of how this method works and how it fails, because it doesn't always work. Thank you very much to Zoe for coming on the stream to tell us about multi-perfect numbers. It's always fun to have people who have seen the stream, got to Oxford, and then turned around and come back on the stream. Thank you, Zoe.
Thank you. Thank you for having me. It's been fun.
It has been fun. Right, and we will be back in 167 hours for another episode of the Oxford Online Maths Club. But until then, from both of us, goodbye, have a nice evening, and enjoy your weekend. Bye.
Bye-bye.